with this slide that I like to use for public lectures for lay people. And I like to introduce, one of our big questions is the energy and matter content of the universe, and I like to claim that only 5% of the energy matter content of the universe is made up of something. Made up of something that we already know, and then there is 80% of the matter content, or 25% of the energy matter content of the universe consists of dark matter. And this is one of our big questions, the nature of dark matter, and if there's a particle physics answer to it. And I wanted to start with this slide because I wanted to vaguely muse whether this is a common interest of astrophysics people. It's definitely of astroparticle physics people and the particle physics community, and it's also a common interest between different experiments in my home institute. So that's why I wanted to start with the question of the fundamental nature of dark matter. Apart from that, the topic of my talk was machines that learn and the quest for the fundamental laws of nature. I originally wanted to talk a little bit more about sort of our own work, but then I ended up with a bit of an overview talk. So I will focus more on the overview and only.
Just a quick thing. I think your mic is a bit, I don't know, too loud or something like that.
Too loud. Okay.
Very good. Look like overturning.
Yeah. Am I saturating? Is this better?
Yeah, I think so.
Is it? Yeah, better. Okay. Thanks. Yeah. So our the one experiment that at least I personally have been most involved in is the Cms experiment. Here's a picture of it, except it's actually not a picture of it. It's actually from the movie Man Spider-Man Into the Spider-Verse. I thought it was very nice how they actually, take from science and turn it into science fiction. This is our real experiment, CMS detector. You see this person here, this guy, Michi Hoch. He's one of my colleagues, an Austrian. It's the experiment is CERN, Geneva. It's one of the big experiments of the Large Hadron Collider, 30-kilometer largest collider in the world. And you see our experiments are quite large. I mean, this is like 20 meters, 5 stories tall. It's about as tall as the Viennese urban buildings here in my, outside of my window. And we take data at, we shoot protons at protons, and we basically make pictures of the collisions of the proton-proton collisions, and we take 40 million pictures per second. And you see, obviously, there's a lot of channels, so it's sort of like a high-resolution 3-dimensional image, if you wish. So we have quite a sizable data rate. This is where I want to go with this introduction. So very, very loosely speaking, we're talking about something of the order of an exabyte of data and something of the order of 1 million CPU cores, not to mention the GPU cores, that we have at our disposal to actually process this data. So we're very data intensive. So machine learning, statistics and machine learning have a long tradition in my field. And as I said, I actually wanted to talk originally more about sort of our applications, but then I ended up preparing an introductory or sort of an overview talk, and I will stick with it. So my revised title of my talk will be Deep Learning Standard Toolkit, the 2022 edition. So what are standard tools? What is admittedly and obviously also somewhat subjective, but what do I think are the standard tools that are here to stay? Because there is so much movement in this machine learning community that a lot of the ideas, pop up and will die out again. And I try to address the question of which of all these ideas that are out there will likely stay. What are the big ideas, and how can we sort of make sense of them in an overview kind of approach? Yeah, so here's the syllabus, what I want to talk about in the next 30-40 minutes. And yeah, feel free to interrupt me and tell me if I should skip something or be slower in something. But my syllabus is as follows. I wanted to recap because I understand that not everybody here is a machine learning expert. I wanted to very quickly go through the very first basics, the very first steps in this neural network. approach of machine learning. Machine learning is not only about neural networks, but neural networks are clearly sort of the big guy lately, as of late, and they are amazingly adaptive. So they do deserve center stage. And then I want to show sort of like the neural, I want to introduce the neural networks the way I got introduced to them 20 years ago when I started my PhD. And then I want to sort of go through what I think are the common tricks that are here to stay. So the first one will be multiple layers, composition, the notion of composition. Then I think a big group of ideas that actually are very helpful are, I will call them symmetries in the largest sense of the word. Then I want to talk about how you can turn neural networks into models that actually generate fake data, because I think this is very interesting for us. Very important for us is we don't just want predictions, we also need errors on the predictions. So I will talk about a bit about what the common tools, but currently the standard tools are in that regard. Then you want to know not only does your machine learning algorithm work, but also why it works, what is the machine learning interpretation methods. And then I would like to shortly introduce, but only shortly, because this is a very recent topic also for me, about machine learning for controlling and calibrating a detector or an experiment or a satellite or something. So this is the big era of reinforcement learning. And then I have some additional topics. I guess I will skip them all because we don't have so much time, but interesting topics are there's a lot of new hardware in the game. It's not only CPUs and GPUs these days. So this is a very interesting development. And then there's connecting all these techniques with more fancy data structures, graphs, and so on. Okay, let me start with a bit of naming convention. It's not much more than that. We tend to think of machine learning as being composed of different categories. This is not all the categories that are out there, but this is a good first initial categorization. We think of, if we have labels, true values that we can teach the machine with, we call the machine learning algorithm supervised. So if we have pictures of cats and we tell the machine, here's a picture of a cat, this is a cat. Here's a picture of a dog, here's a picture of a house, here's a picture of something. This we will call supervised learning. We are the supervisors. Yeah, we know the truth, and the machine is only supposed to learn, our truth. Then if we have algorithms that don't have labels for whatever reason, if the machine has to find out some structures behind the data without any labels, without any supervision, we call it unsupervised. And if it's about controlling, if it's about you being an agent in an outside world and you being able to take actions, the agent being able to take actions in this world, we will call it reinforcement learning. So a machine that learns to play a game will be a reinforcement learning algorithm, or a machine that learns to drive a car. That will be the typical applications. So this is number one, classification of learning algorithms. And number two, the naming convention that I like and I will use throughout the talk is, now let's drop the reinforcement part and focus on the supervised part, because that's, mathematically speaking, at least, that's probably the easiest part. I will always talk about, so we always want the functional dependence between some label Y and input data X. So I will always refer to the input data as X. That could be, for example, the images, or the satellite images, or the images of your CCD camera or whatever. And the labels Y, they can come in integer values, like 0 refers to a cat, 1 refers to a dog, 2 refers to a horse, in which case we will call it a classification problem. Or they come in real numbers, like, you have the image of a person, you see the face of a person. The machine has to learn to predict the age of the person. That is a problem we will call regression. But we don't actually care so much about these differences, whether it's classification or regression. from a machine learning and statistics point of view, the difference is not so large. It's very similar. There are small differences we will make. I will get to that, but it's actually a very similar tasks. One guiding concept that I would like to introduce, at least it helps, at least for me, it's helpful sort of to make sense of the slides and the different approaches and everything, is to be thinking in terms of probability distributions and particularly conditional probability distributions. So if a machine has to find a probability underlying in some way or some aspects of the probability underlying your data, P of X, we will call it unsupervised learning. So I'm saying the same thing, just with the notion of probability distributions. Our usual classification and regression problems will be finding the probability distribution or aspects of the probability distribution of Y given X. Given the data, find my label Y, predict my label Y. That's classification and regression. And later we'll also come to data synthesis, to generative models, in which case we turn this around and we want, in one way or another, find the distribution of our typical data given the label. This we will call generation or generative model, okay? But the overall naming convention, Y is always a label, X is always data. So let me reproduce. I should have a clock here just to make sure that I don't go completely lose myself in like one of the slides. Overall, if this was a lecture, I would take, I think, an hour to go step by step through this. Here, I will be a lot quicker. Sorry for everybody who is not so familiar with the whole thing. The number one thing is the notion of the multi-layer perceptron, which was introduced in the, I don't know, 1960s or 50s even. This is sort of like the most basic cornerstone of neural networks and machine learning, novel machine learning, modern machine learning techniques. And the idea is as follows. Here we again have our input X. This could be, you know, the picture of a cat again, or a dog. And a neural network, the most basic neural network has this architecture. What it does is it has weights. And let me get to the next slide because you already have a lot more info. So we have our input here, we have our weights here, we have a dot product between these two guys. So we multiply the input with the weights. These weights, I call them weights, they're parameters. Yeah, the input gets multiplied with them. And I will later argue that these will be changed during the learning procedure. So the network, when learning, these weights will be adapted. What I have there, so you see all the data will flow very much in that direction in a prediction step. When the neural network makes a prediction, that's why it's called feed-forward network, these types of architectures. The dot products get sort of stored, or they all enter an aggregation. I will call it an aggregation function, usually a sum. And so far, there is nothing that is nonlinear here. So, you know, remember our problem that we actually have is we need to learn a functional independence between our X and Y. This is the overall idea. We want this, there's a functional independence. We want to get that from the data and not construct it, you know, by hand in closed form mathematics. We want to understand, we want to learn this functional independence from the data. So the data went into an aggregation function, and what happens then is you need some sort of a nonlinearity in this whole procedure, or else you cannot learn a nonlinear function. With only linear operations, you cannot obviously learn a nonlinear functional dependence. And this actually happens in the so-called activation function. Yeah, the very first activation functions were these typical sigmoidal functions. And the metaphor from biology obviously is that there is, you know, this is a neuron. These are synapses or axons. Information comes in here, gets stored. The electrical potentials get added up from the synapses. And then the neuron either fires or does not fire, right? This is the biological metaphor. The reason why we actually call this a neural network and not just a mathematical function. Yeah, so you have an activation function. And what you do then is the activation function will turn into a predicted label, my predicted label could be, you know, this is a cat with a certain probability, if it's a classification, or the age of the person is 65. And then I'm talking about supervised learning. So I have a Y true. I have a true label. I can compute a so-called loss function. That is a function that tells me how far I am, statistically speaking, from the true labels. In the case of a regression, a very typical, very simple choice would be the mean squared error, right? So y minus y true squared. This inarguably becomes larger the further away I am, the bigger the error I make. Okay, so this function really tells me how good I am. And what do? What is learning? Well, learning is nothing else than minimizing this function, this loss function, in a gradient descent algorithm, right? So I compute, I can write it down like this. I try to find those weights. The weights are the ones that the machine is allowed to adapt, to change in the learning. I try to find that set of weights that minimize my loss. Yeah, to make sure the error of my predicted value is minimum. This is all. Yeah, usually I do this, or in neural network, I almost always do this in a gradient descent fashion. And everything else that enters here is lots and lots of technical details. So I'm sorry, this is supposed to be a video clip. Don't know why it isn't, but never mind. You would actually see, you know, like a physical, like a point rolling down in this energy landscape. This is the energy landscape, or the loss, you know, this is a visualization of the loss function, L. And you would actually see how in the gradient descent method, when the network is learning, sort of a ball is rolling down and trying to find the lowest point in this energy landscape. I always think of, when I think of gradient descent and minimization problems, I always think of sort of a landscape. You guys are in Graz, so the Alps are near. You are somewhere in the Alps, and you let a ball drop, and the ball goes in a gradient descent to find the absolute minimum. That would be the river, I guess, the Mura or something. And yeah, this is how I visualize the mathematics of learning in neural networks. And there is lots and lots of technical details that enter that I will skip for this talk. They are important if you actually do the job, but for this talk, I find them not super important. One of them is that usually you normalize the input before you actually have it enter the neural network. The other point is you have a choice in the activation functions. Some choices are better than others. You can do tricks with the learning rate. In this gradient descent method, you can add additional terms that actually make it more robust, and so on and so on and so forth. There's usually, you add a penalty term for using too many neurons. Yeah, but these are all technical details that you have to learn when you actually implement machine learning. But, you know, for our overview talk, we sort of, we shrug it off as technical details. And it actually shows, I will also have, I will try to make connections with sort of local contributions to the machine learning community effort. It actually shows that if you have this type of an architecture, which we used to call multi-layer perceptron, and if only you add a big enough so-called hidden layer of neurons, so you have one layer of neurons that are, we call them hidden because they're not input neurons nor output neurons. If only you have one of these layers, and if you only have a nonlinear activation function, if only this layer is large enough, and if only you have enough amount of data, so infinite amount of data, you can, in principle, learn any functional dependence y equals f of x. The formal proof of this is actually remarkably simple. It was given by Sibenko in America in 1989, and one aspect actually got added by a local guy who is at VU Wien right now. He was also at that time by Kortolnik in 1991. So this is the universal approximation theorem. It's actually quite powerful because it tells you, well, with this very simple neural network, we can learn any functional dependence. So, and this is the end of my talk because we solved the problem, right? All supervised problems are solved with this type of neural network, right? Well, the answer is obviously no. In principle, yes, but in practice, no, because in practice you would have to have infinite amount of data, and your hidden layer would have to be allowed to be infinitely large. So what is the problem? Or let me rephrase sort of the same question I tried to allude to. Let me rephrase it in a different context and phrase it differently. Let's say we have the set of all possible images, high definition. So high definition is 1080p, right? So that consists of 1920 times 1080 pixels, 3 channels, red, green, blue. So the set of all images, of all possible images we can have in high definition is given by this number. So the multiplication of this is 10 to the 13. It's a pretty large number. So how does, there is one paper that asks the question with the words, why is deep learning so cheap? How does this work at all? How can we do classification if this space of all possible input data is so huge? It shouldn't work, right? With a training sample of 1 billion images, this shouldn't work. And just by simple laws of statistics. So why does it work at all? Why does Google actually manage to predict this? Is I don't know if it's Google or somebody else. You see that they label everything. This is, I don't know, a place in New York City. And you see that the machine labels everything correctly. How can the machine learn this from a very limited set of input data? And the answer brings me to what I think, and I try to speak very high level in terms of these concepts that we introduced. Number one is additional layers. Back when I started 20 years ago, you know, we were hung up on this universal approximation theorem. We felt like, okay, one hidden layer can learn anything, so why would we introduce several? And the answer is, I'll need a few more explanations to how to make this work. But the overall concept is that if you have many layers and if you do it right, then you can learn a hierarchy of representation of your input data. So here's your input data. We still have a feed-forward network. So the data in the prediction step, goes from here to the right, from the left to the right. And here we encode in the output nodes, we encode our predicted labels like cat, dog, or whatever, or an age or whatever. So one aspect is the notion of composition. A function can be, you can construct a mathematical function as a composition. A function is a function of another function and so on and so forth. Y equals f of g of h of x, or a notion of, computer vision. A cat is composed. Here's a cat. I'm an awesome drawer, I know. A cat is composed of legs and the head is composed of eyes, and so on and so forth. So you have this notion of composition and hierarchical representations. This is, I think, one very important ingredient, but this alone is not sufficient. The next important ingredient, and here I probably deviate a bit from how I introduce it right now. Usually the next thing one would say in computer vision is the notion, in computer vision particularly, the notion of convolutions. So instead of fully connected neural network layers, fully connected means that this neuron here talks to every neuron in the next layer. That is what we call a fully connected architecture. In the convolutional neural network, we have these kernels. So we have small matrices, and the weights in the matrices are learned. These are the ones that the machine will adapt in the learning step. And these matrices scan over the input image, and they share the weights. In that way, these what we call kernel, this is called a kernel. These kernels can learn to represent edges and nodes and so on and so forth. And here in this talk, I wish to give it sort of a larger context, of a more generic meaning, attach a more generic meaning to it. And that is the meaning of symmetries, invariants, equivariances, and groups. So what I mean to say here is that the convolutional neural networks, this is a typical architecture. This is typically how the architectures look in the computer vision community. So you have your input, then you have multiple layers, right? Because composition, as I said. And in each layer, you have like multiple kernels that scan your image, and each kernel can learn something. They can learn to represent a line, to represent an edge, and then the combination. Then you have something called subsampling and pooling. I don't want to go into this in too much detail, but then the machine can learn in the next layer. The machine can learn to represent combinations of these primitives, of these edges and lines and circles, to represent an eye. And from this, the machine can learn that the cat is composed of eyes and legs and whatnot, and noses, and so on. So composition and these convolutional kernels. And the bigger concept that I wish to give here is that what you introduce with this is what we will call invariances and equivariances. The idea is you have a translational invariance, meaning, or your problem is actually a translational invariant problem. If the cat is here, or you have an image, whether the cat is here or the cat is here, in a multi-layer perceptron, the machine would have to learn this separately, would have to learn to identify the cat here and to identify the cat here. But with these convolutional layers, what you introduce is a translational invariance. The same kernel will identify the cat whether it sits here or here. So this is the exploitation of one specific symmetry in the context of neural networks. Convolutional networks. This is the detector again. Just the connection always with particle physics. Of course, we have detectors that work very similar to cameras. So we use convolutional networks to differentiate in that specific case, for example, between two different types of particles that actually, there is a proton coming in here. They clash, they produce a Higgs boson, the Higgs boson decays, and the decay products actually enter and are being recorded in these detector structures. And here you use machine learning to identify one particle to say, okay, here, this was actually a W boson or something, or this was a W prime boson, a hypothetical particle or something else. Yeah, maybe I skip the LSTM because how am I with time? Yeah, I think I have to skip it. For time series, we wouldn't use convolutional kernels, we would use recurrent neural networks. But one aspect is also here, we exploit the notion of asymmetry, the time invariance. And the bigger picture, I think, and I wish to concentrate on this, bigger picture is we have this notion of invariance and equivariance of a network. Invariance of a network is I shift the cat. Yeah, P is my shifting operation. P means I shift the cat to the right, for example. Classification should be the same. It should still recognize it as a cat. Equivariance of a network would mean I shift the cat and say I have a machine, like neural network that is being tasked with identifying the position of the cat. Then the final position of the cat should be the same as the shift, right? F of P of X should be P of F of X. Right, I shifted 10 centimeters to the right. My network should give exactly these 10 centimeters as the offset in the regression problem. This is called equivariance. And so the bigger picture is, can we, and I think the more interesting question is, convolutional networks and recursive neural networks exploit some symmetries, right? The convolutional network exploited the translational symmetry. But bigger question is, can we exploit symmetries more systematically? Or I'm thinking, I don't know about you guys, but we're in close contact with cosmologists very often. So they have cosmic microwave background, for example, is a 4 pi data set that closes, it's a picture of the whole sky. So I imagine that they will be working with a set. Sort of their symmetry is the set of all rotations of this 4 pi sphere in group theoretical terms, I know they have funny names, but this will be the SO3 group, the set of rotation matrices in 3 dimensions. And the question is now, if you have a fundamental symmetry in your data, mathematically, like how can you build in these symmetries or these operations? How can you build these equivariances fundamentally into your architecture? And I don't want to discuss here in detail how exactly they do it, because it's not so trivial. But I give you a lot of links, and as a result of their work, actually they have some, for example, a network that is by definition E3 invariant. Here, for example, this one, E3 is the set of all operations in 3D Euclidean space that leave distances unchanged. So it's a set of all rotations and reflections and translations in 3D space. That's something that you would often want in a network. I imagine, for example, in the case of, I don't know, cosmic wave background, for example, you will want an SO3 invariant network, which is also already available. So if nothing else, then at least this group theoretical jargon helps us more quickly identify already ready-made solutions by other people of networks that have properties that are favorable, that we want. Here is an example of something that we're starting here in Vienna. I'm starting with a PhD student. We have now, for the year 2030, we want to change this part of the detector, a so-called calorimeter. I don't know if you guys use calorimeters. They measure energies of particles, and replace them by silicon detectors that have this hex shape. So here we would have a Z6 symmetry. It's the symmetry group of all rotations by 60 degrees. And there is already a solution for that, actually. It's the HEPHY experiment, the telescope array. And I imagine these hex-shaped detectors, they seem to be popping up everywhere. I think James Webb also, at least on the popular science pictures, it also has these hex-shaped structures. So you want a convolutional network that actually works on these hex-shaped structures. And in some sense, you want them explicitly or implicitly. Very often you want them to exploit this Z6 type symmetry. Yeah, which brings me to the next tool. I'm very late in the game, I'm sorry. I try to be really, really concise and short. We have all these nice neural networks now. Let's go back to the nice multi-layer perceptron type fully connected network. And one trick we often play is, in one way or another, we turn the network around. So usually you have a high dimensional image, high dimensional input data, like an image, for example, and you have a low dimensional label, and you want to know P of Y given X. But sometimes, and I claim in science actually also very often, you want P of X given Y. So you, in one way or another, want to turn this around, this architecture, and you have the labels as input, and you want to generate fake data, synthesized data from the input. And this is, there are a few architectures that do this, but the overall name I will give to this is tool number 4, generative models. These are like, they generate data. And yeah, maybe I go a bit faster. This is one of these generative models applied. I mean, these are very famous, right? This is all fake, deep fakes. None of these people have been born. So this is a generative model used in the context of convolutional neural networks in computer vision. And what do I... yeah, maybe I still do introduce this, because otherwise it's too high level. So the way the first one of the oldest sort of grandparents of generative models, if you wish, are so-called autoencoders, and the autoencoders have this type of architecture. So it's like a multi-layer perceptron here, right? You have a high-dimensional input data, you have a low-dimensional layer in between, but what you do then is that you reverse this part of your network here. Yeah, so you get again high dimensional, but same dimensionality as your input data. And you put your loss, you set your loss to this square of the difference between your output data and your input data. So what the machine learns is the machine has to learn to reproduce its own input, but you send it through a bottleneck, right? Here you're lower dimensional than in the input and in the output layers. So the machine has to learn to compress, right? It has to find a lower dimensional representation of your input in order to be able to reconstruct the input from this low dimensional representation. So it learns to compress, or sort of it goes with the philosophy understanding is compression. So it has to understand something in the data or else it couldn't compress. And the way you turn this into a generative model is with another trick that I will skip here. It's called variational neurons, where you then turn this part into a generative model. Yeah, so you have a label, you plug in your label here. You have to have, as I said, another trick that I will not go into details, but you have a network that produces fake data, synthesizes data. And this is how these types of algorithm works. Here is another such algorithm where two neural networks try to compete against each other. So you have one of these neural networks that has this architecture where you start with a low dimensional space, go to a high dimensional space. This you will also call the actor or the generator. So this neural network learns to paint like Picasso. And then you have another network that has to learn to differentiate between the Picasso and your fake Picasso, and they compete against each other. And by competing against each other, they sort of turn really good. Here's an example in particle physics where we are making use of such an algorithm. And here's another example that is quite nice and illustrative of why this is very useful for all sorts of our hard science questions, because here the machine generates fake celebrities or fake faces, but it also comes with conditions, right? Here you change the condition of what you're generating. So here you're putting on glasses to that woman. Here you're changing from an Asian type face to a European type face. Here you grow a beard and so on and so forth. So these types of images are variational autoencoders, but including the notion of conditions, so conditional variational autoencoders. And this type of generators, I think we have a lot of use. I assume in astrophysics, astronomy, as much as in particle physics, because I would want to know, please machine, give me the distribution of all images. In our case, for example, in our particle physics case, we would ask, give me the distributions of all pictures of proton-proton collision, but turn on supersymmetry. But assuming that supersymmetry is true, for example, is realized in nature. And yeah, this kind of synthesized data we need all the time for our statistical inference. Here's the link to conditional variational autoencoder. Next, I am running super late. Next is one other aspect that we need in the hard sciences. I think we need much more than Zalando or something, or Amazon, I assume. What did I know? Is that we need to also quantify the errors of our predictors, right? We have a neural network. The neural network predicts, classifies pictures of stars in, I don't know, inhabitable or mainline, not mainline, whatever. And we also want uncertainties on these predictions, because I mean, at the end of the game, we're still doing science and not generating fake celebrity or fake images or something. So we need to quantify the errors, and the errors have two sources. In these supervised machine learning setting. The one error source is the error on the inputs. This we can propagate. The error on the input propagates into into an error on our classification. This we will do with our regular methods. So we have, typical normal error propagation, or we can, change according to the errors on the inputs. We wiggle with the inputs and see how much the output changes. This is the usual tricks we do. But then there is also an error that comes from the neural network being imperfect. And this is called an epistemic error. The machine learning people, I'm not super happy about this, but the machine learning people have their own jargon. I will call it systemic in statistical errors. They call it aleatoric and epistemic errors, but they mean something almost very similar, except that their statistical error, aleatoric, alea is the dice, so it's the error coming from randomness, but we will call this systematic. And what we call error from randomness, they call epistemic. So the naming convention is a bit difficult, but the question is, can we quantify the error that comes from the neural network being imperfect, not the error that comes from the input data being imperfect? And I think currently I see sort of like one main line of how to do this, a standard technique, standard tool for gauging, estimating the error from the network, not from the input data. And that is by making the neural network. The complicated version is you make the neural network Bayesian. As a repetition, Bayesian statistics is a statistics where you not only give probabilities, assign probabilities on observable parameters, but also probabilities on theoretical parameters. This has a frequentist interpretation. You can say this I will measure so and so often. This has not a frequentist interpretation. It only has a subjective interpretation, a Bayesian interpretation. And what you do is, I will also skip the details. You replace all the weights in your network with distributions of weights. And these distributions are Bayesian probabilities because the weights are theoretical parameters. So it's P of W given the data. And that way, sort of, you account for all the probabilities, all the errors that come from the sort of like imperfect weights, if you wish. And that way you can sort of propagate and get a final answer to what's the error on your final classifier or regressor from the network itself, not from the input data. The way you do it is actually very complicated and it takes a lot of time. So you have to sample, so rerun the neural network many, many times. But that's one standard technique. There is a shortcut, however, and I will focus on that one because that one's easier to explain. And the shortcut is that in this publication, or this one here, the authors showed that a good approximation for these Bayesian errors, for these errors on the classifier, on the regressor, due to the network itself, can be approximated via dropout. Dropout has been introduced already before in the training. So already before 2015, people randomly canceled neurons in the training phase of the neural network to make the predictor more robust, to make it not depend too much on individual neurons. Here, you apply dropout on the prediction, not on the training. And by applying dropout many times on the prediction, you get an estimate for the Bayesian error of the classifier from the network. They actually showed this somewhat rigorously in this publication. So this is the way to go forward, I think, at least for now, for estimating errors of your neural network itself. And then the next tool will be, try to be super fast. The next tool will be, so now you have a neural network. The neural network, let's take this example. The neural network learns to identify horses on pictures. So you have a classifier. The classifier tells you, yes, there is a horse on the picture and the horse has a rider or whatever. And now you want to know, you also want to, say your application is in medicine or something, but also in our cases, you want to understand why does the network, you see that it's working. Now you want to know why it's working. You want to understand what has the network learned, and these are called interpretation methods. There is already a sort of an entire slew landscape of several interpretation methods. I very quickly have like slides to introduce two very simple ones. And a very simple one is you have a classifier. Classifies it tells you there is a horse in the image, and what you do now is you go pixel by pixel. You change the pixel of your input data, and you find out if it actually has an effect on your classifier. And if it does, you make a heat map. You sort of highlight that pixel in red, and if it doesn't, you sort of low light the pixel in blue or green or so, and you get a heat map. And here is this example that these guys in that publication actually came up with. The classifier learned to classify a horse, and then with these heat maps, they actually found out that what the classifier learned was not to identify the legs of the horses, the number 4 legs of horses, the head or anything like that. No, the training sample, actually, all the horses in the training sample came from the same source, and the source had a label. They actually labeled these images, and the neural network understood that as soon as there is this label in the image, it has to classify it as a horse. So with these interpretation methods, you found out that the horse actually did learn something, but it actually learned an artifact, not the thing you're actually interested in. So this is very useful. The other interpretation method that is actually more successful lately, I think, I will skip. There are many of them, but here you actually see that the goose is identified by the outline. So that's very nice. That's how it should be. And the final thing that I think will be more interesting in the future, I think our communities have only started in that direction. I don't yet know any very successful approach. If my PhD student Felix is already here, then I would delegate this to him. I don't see if he's here already. He has another meeting, but he's actually starting to work on this in a different experiment, in a dark matter search. So Felix is working in an experiment beneath the Caranzasso, the mountain near Rome. And they have a smaller, for our scale, smaller detector. The question is, a dark matter particle enters the detector, recoils against a nucleus in the detector material, and you want to pick this up. In order for this to work, you need to fine-tune, calibrate the detector very well. And that is a typical reinforcement learning problem. And reinforcement learning means I will only sketch it out. It's also very new to me. I don't yet have a lot of any experience with actual real applications. We're starting this now, but in the reinforcement learning context, at least the vocabulary is clear. You have the notion of an environment. In our case, it's a detector and the magnetic field and the temperature and all this. You have an agent. So the agent means you have an active component. You can change, you can set actions. Or you can enact action. The detector is always aligned and calibrated, and if there's something wrong, you change, and so on and so forth. And you set actions, and in our case, for example, the actions will be changing the sort of a magnetic field that is supposed to account for the magnetic field of the Earth, and so on and so forth. You can change. You have superconducting detectors. You can change. So you have to gauge. You have to make sure that they're right at the temperature, at the phase between superconducting and normal conducting, and you can change your working point by changing currents in a heating resistor, and so on and so forth. So you can set actions, and the reward in our case would be, the scientific output. You want to maximize the scientific output. And very often you have a long-term and short-term reward. The long-term reward is you need stability of your detector. The short-term reward is you maximize sensitivity of your detector for some physics phenomenon you're interested in, like the interaction with a dark matter particle. And and I don't want to go too much into this, but this is obviously very interesting for a large number of people, including all the car industry in Germany. The default method is a method called Q learning. Q because your reward function actually is called Q. But basically what you do is you need to learn a policy. The policy is a function that maps the states onto actions, right? Given a certain state you're in, what action should you take? Should you increase the magnetic field? Should you decrease the magnetic field? Should you gear to the right? Should you go to the left? Should you hit on the brakes in the car? And so on. So this is what you need to learn, the policy. And the reward is what you need to maximize. So you see our usual, we phrase as we phrase everything, we phrase it as an optimization problem also here. And the standard is Q learning. There's also by the Linz people, we have a very nice, the author of the most famous recurrent neural network architecture, the LSTM, is a professor in Linz, it's Sepp. And they also came up with an architecture, here's the paper, where they actually learn the reward function with a recurrent neural network, and for the rest use something very similar to this standard. And I think I will skip the honorable mentions. The only thing is, maybe 3 sentences. So one thing that appeared very recently that I think is very interesting for a lot of people is you can generalize convolutional neural networks to work on graphs. So in a convolutional neural network, right, you had pixels and you had a kernel that slides over the pixels. And for example, if you want to learn if certain biomolecules, large molecules are toxic, you do something different, except you think of the molecule as a graph with edges and nodes. The edges, then the nodes will be the atoms, and the edges will be the connections between the atoms. And you would want to know, you have a very complicated molecule, you would want to know if there is any subgroup that makes it toxic, and you use something similar to convolutional neural network and slide over it, and the neural network that way can learn if any subgroups make the molecule toxic. And graphs are something that are also, this is molecular, something that's for more rigorous mathematics is interesting is graphs are, of course, also the structure of mathematical equations. You would, in a computer, a mathematical equation you would think of as a graph. So you can also think of exploiting this notion of graphs and graph neural networks to employ it in the context of symbolic regression. So symbolic regression means you have a large chunk of data, say movements of particles or something, and you want to learn the machine should find a closed form equation of the physics behind your data. So this is a paper by Max Tegmark at MIT, where he does a lot of symbolic regression. He feeds the neural network with data about moving particles, and you actually see, this is a very ideal case. He's a theorist, not an experimentalist, so he has ideal data. So you see that the neural network actually learned the relativistic equation for kinetic energy, and it even learned the classical approximation of the relativistic kinetic energy, mv squared over 2, and then it learned sort of an in-between approximation also between the classical physics and the relativistic physics that, yeah, we as humans would not so easily have come up with. But the machine just, finds a closed form equation for your data and it just pops up. And here he plays sort of the complexity of your equation against the precision. And there is an in-between approximation that is a bit better than a classical, but not yet relativistic. So these types of things, I think, are very interesting for people like us, and are only very recently sort of appeared on the radar. Yeah, and then there is also hardware. We use, so far we've done, most of us have done all the neural network inference on CPUs and GPUs and TPUs, and there is all sorts of new diversity in hardware that is sort of showing up that is very interesting. Quantum computing particularly, because we can also all of a sudden use sort of, instead of a classical gradient descent, we have all sorts of quantum based algorithms that might have favorable attributes that I will not go into. I think I will stop. My very last, and then I stop, is actually a work that Andre and myself and another colleague are doing. It's not neural network based, but it's also a kind of learning. And we're asking ourselves, we have a large database of experimental, of publications, of papers, of LHC results. And this here is a very nice, a very concise description of the fundamental laws that govern energy and matter in our universe. And we're wondering, what do we need to change in these parts of the equations? Which part to gain sort of, to go towards the next fundamental theory in particle physics, that sort of the laws that govern the energy and matter in the universe, because we know this here is not complete. For example, dark matter is not accounted for in these equations. So what do we need to change? And we let the machine actually decide, or what we have to add or change in our fundamental description. And we hope that way we find sort of the next fundamental, the next deeper level of our understanding of the universe. And I stop here. Thank you very much.
Thank you very much. Absolutely amazing talk and overview of everything machine learning in 1 hour.
Yeah, sorry for taking so long. Okay.
No, it's not a problem at all. It was really awesome.
Okay.
May I propose that we take a 5-minute break here, so that we can
absolutely
get some coffee and then think a little bit about questions, and then in 5 minutes it's like 1 after 3 p.m. now. So like in 5 minutes we meet again. Okay.
Avec plaisir. Yeah, absolutely.
All right. Shall we start with the questions?
All right. Yeah, there are some in the chat I'm seeing.
Yeah, I think Peter had the first one.
Uh-huh.
And then we just go on from there. Yeah, just Peter,
Yeah,
go ahead.
yeah. So why do okay, sorry. Yeah.
Yeah, so thank you for the interesting talk. Maybe one comment is that astronomers are actually not particularly use, as well, maybe they do, but not so much images, but most of it's maybe rather something like light curves or some signal as function of time.
Nice. Yeah.
Or maybe some spectrum also. So like a one-dimensional thing. Probably the techniques are probably quite similar. But what I actually wanted to ask you is the following.
Yeah.
If you're talking, you are talking to people who have little understanding of machine learning in general. So most of us, this is new to us. So from your experience, how would you say somebody is coming to you and has a problem and would like to ask you, is this something that is solvable, or how should I go and learn this kind of stuff for myself? What would your advice be?
Difficult question. Yeah, I mean, for like number one, for time series, I actually skipped this because I thought you guys would be more in thinking like computer vision people. But recursive networks is actually the one thing where sort of that excel in time series. Felix has a lot of experience. He's here, so he can also comment. This is actually one of his works. Apart from this, very difficult. I think one aspect, I think we're doing basic science, right? We're not writing predictors for Zalando for shoes. So I think we should always stay more at the statistics side than the rest of than many parts of the machine learning community. So I would always want the students to also have a decent understanding of statistics, and not just the machine learning part, because I think we always have more. For us, the difference is fluid between machine learning and statistics. We very often write ML/stats, machine learning/statistics. But for us, it's sort of the way we think of it is statistics is more model-based, more rigorous, more probabilistic interpretations, and machine learning is sort of more model-free. And we tend to be always a bit more on the statistics side than the rest of the machine learning people, like the natural language processing people. So that's the only thing that I would find important for the students, that they always, that they always understand that if they can use more rigorous statistical methods, they should. That's one aspect. I'm not sure if it's helpful. Felix, do you have anything else? Felix is here. Yeah, so.
Hi. Yes, I think mostly you summarized it very nicely, I think. Yeah, but also machine learning. So if I understood the question correctly, then it was also like how to get started within the field.
Right. Right. Sorry.
And I think there are few fields where it's so easy to get started just by yourself and by Googling stuff. Because I mean, right now there's a huge hype around this topic. So there are probably more tutorial blogs than people who can actually apply it. So I mean, a few years back when I started dealing with these very simple neural networks, I mean, you can very easily find some tutorial code which you just plug into some Jupyter notebook and start playing around.
Yeah, no, I mean, it's maybe slightly beyond that state. So I mean, many of us are thinking now, should I go into this direction? Should I put effort into trying this out? So I think what we need is some kind of demonstration that things are actually working, that you get motivated and say, oh, wow, this is actually impressive. So why shouldn't I try that myself, at home? And then the other thing is some kind of maybe quick assessment whether it's actually worth it. So that certainly depends on the problem, right? So there are problems that are suitable and problems that are not suitable. And I think what we need would be some kind of advice.
Yeah, I understand. Yeah, some problems are too easy. Yeah, so if you find a functional dependency because you know physics, you don't do machine learning, right? I mean, if I have, my problem is I shoot an arrow in the sky and I want to predict where it lands. I understand the physics. I probably should not use machine learning, for example. Because I understand too much. And some problems are too hard. If you want to use the LSTM to predict the stock exchanges, you will fail because it's too hard. So where machine learning comes in, basically, is sort of somewhat in between, where the machine can still extract something, but it's too difficult for you to create a very a concise model from first principles. In between is where machine learning is really good. Huh?
Yeah,
roughly.
So what I read is, it has to be very complex. Otherwise, you probably find easier methods to solve it.
Great.
So then say the number of trainable parameters or so must be relatively large. Otherwise, it's not an interesting problem. And the other thing is that you need the availability of lots of data.
Yeah.
Because this is, in the end, when you only have a few examples to learn from, this is not a good problem.
Yeah, that is absolutely true. Usually, very often, machine learning is all about beating your problem down with with huge amounts of data. This is very often sort of the summary of machine learning. Not always, but very often, yes.
Maybe if I can add one comment. So I mean, a rule of thumb is if your data has really many dimensions and very strong correlations between these dimensions, then it could be worth to try, for instance, a neural network. Because I think this is also intrinsically a bit connected with this curse of dimensionality. So that for many classical statistical fit models, your computational cost grows exponentially or about exponentially with the number of dimensions in which you try to work. But for neural networks, this is just not the case. And for instance, images are a very good example because they have each pixel is one dimension, and obviously the pixels are very strongly correlated.
Okay, thank you.
And all this also applies for generative models. So usually we need a lot generative models all the time. We just have a different name for it. At LHC, we call it simulation. We simulate, right? We simulate the physics. This is a generative model because we know all the physics that enters, and in the end, we want to know sort of if supersymmetry, if a certain theory is realized in nature, how does it affect our observations? And if we understand everything well enough about how the data come about, we don't use neural networks, we write a simulation software. But now we see that sometimes we replace our sort of our very concise physics knowledge, our simulation software that we write, step by step with generative model that actually extract this from data. And I think the pros and cons are, I guess, obvious. The con is that you understand it less. The pro is that it can learn some effects that you would not be thinking about, some very small details that it extracts from the data that you would be having a very hard time modeling. So this roughly here is sort of the niche where machine learning enters. Too complex already to do it, for you to find things out yourself. Not yet complex enough for the machine to still learn stuff. Yeah, no idea how this translates into your fields. Yeah.
Make a comment, and an application in space physics is that you automatically classify, for instance, in time series, things where it's just cumbersome for a human to label things, and then you just try to automate it with a machine learning model, for instance. So that's kind of a more obvious thing that you can do in astrophysics or in space physics. That's
right.
something we're also working on.
I imagine you want to have you do statistical inferences on millions of pictures of stars, something along these lines. And you need to classify them or something, and you will not do this by hand.
I work on solar wind physics, and like when we see like a solar storm in the data, we want to automatically the computer tell us, okay, there's a solar storm in the data, and that's actually, so we have some more questions, but maybe I'll just put mine right here. There was a recent trend that if you don't have enough data, which is sometimes in space physics or in astrophysics, because you don't have infinite observations and you don't have millions of people buying shoes online, then you just
right.
generate. So to overcome this problem that you don't have enough data, you start to generate synthetic data with simulations. I just recently read that like in an MIT thing. Can you comment on that? Is like that's something big coming up, or
I mean
this like that?
This is something we do all the time. Okay. So we have an exabyte of data, and the majority of this data is not the actual we have actually in that sense we have more than really an exabyte of data, which is a lot. It's a million terabyte. It's a lot. And the majority of these data is actually not the actual measurements, but simulated data, and be consistent, consequently compare the actual measurements with all the simulated data. Because you in one way or another you go through scientific hypotheses, and they translate into different simulated data. And then you compare against all the simulated data, and you go like, okay, my real data are most similar to these and that kind of hypothesis data from this and that hypothesis. So the simulation actually we have 1 million CPUs, we have a lot of computing power, and the majority, like 80% or 70% of this computing power is spent on simulating data. So here, very often, a big trend for us is now that we have simulators. They work very nicely, and now we use generative models only to make this faster. This, for example, is already a big bonus for us. So learning to generate fake data, that correspond to specific hypotheses is for us is a huge endeavor.
No, that's something I am also thinking about in applying. Especially in physics and space physics. Actually, there is this week, I think there's a machine learning conference on machine learning in heliophysics. So it has come up quite a bit, at least in space physics already. And we're also using that for specific problems, and that's definitely something. I just see that you're doing it on a much larger scale already than everything that's at least what I know from heliophysics. LHC is really big data. And of course, in space missions also take a lot of even more data, increasingly growing data, but it's not comparable to CERN in any way. I think there should be a few orders of magnitude more that you get from LHC. We're
a very centralized community in the sense that we work on like a handful, like on one machine, 10,000 people, 3,000 people on one detector, and huge amounts of data. So we actually some of our colleagues can specialize in really, really small technical aspects, like this generation of simulated data.
So any more questions? I saw one in the chat where I think it was Christiane maybe. I'd like to know what lessons the speaker learned from applying neural networks to his specific application, vector development. So like more on the, I think it was the last thing that you talked about, right? Can you maybe elaborate a little bit on this?
Okay, my last one was like this application in completely just theoretical physics. But detector development.
Or this is about reinforcement learning.
The reinforcement learning, yeah. So Felix is actually can say more about this, because Felix has already like sort of started to get his hands dirty on reinforcement learning, contrary to me. So Felix, do you have anything smart to say here?
Yeah, dirty is a good keyword actually. I mean, yeah, probably. Okay, it's hard to summarize everything with a few words, but okay, we as physicists want, if you want to use this in an experimental setup, then you have to deal with a lot of real-world problems, which you don't encounter if you use this to play computer games or something. And there is actually, this is even a niche, but also a field of research within reinforcement in the reinforcement learning community, namely to bridge this simulation to reality gap.
Right.
Because typically these reinforcement learning agents, I mean, they are really efficient in finding optimal strategies, or at least very efficient strategies, but they need huge amount of data, in the sense of that they have to for a long time try different actions and observe the responses of the environment. And with a long time, I mean, usually you cluster this in discrete time steps. I mean, millions and millions of actions and responses. And for instance, in our experiment, this is a cryogenic experiment where you control some temperatures, and usually you have to wait for a couple of seconds until you can observe the effect of your action. And then, I mean, you can calculate how much time this would be if you try 1 million of actions and every action takes like 5 seconds or so. So this is not feasible to do this on the actual thing, so to train your agent on the actual thing, but you have to build some realistic simulation where you train your agent, and then you have to design this simulation so realistic that the agent, when he can do the actions on the simulation, also can do it in the real world. And this is, of course, a huge challenge, because the real world is always more messy and more complicated, and there are more unexpected things than in the simulation.
Good point, yeah.
So I think for physics, in our case, especially experimental physics, this is one of the major topics, and also the major reason why not everyone uses this already.
Right. Yeah, that's a very good point. So Felix thinks that he will do this for this dark matter experiment, and we think that he will spend 90% of his time getting the simulation right, and then spend actually fairly little time actually applying the reinforcement learning algorithm, because there's already ready-made solutions you can pick and try. Right, Felix? This is how we think of it.
Exactly. Doing the reinforcement learning will take like a week or so, and building the simulation will take a PhD or so.
Exactly. That's I think a good point too. And this is different from even 5 years ago, let alone 10 years ago, that you have already like these neural ready-made solutions, ready-made reinforcement algorithms, ready-made computer vision algorithms that Google has open sourced many of their neural networks, and Facebook and so also. So what is different is that you can now try something that is actually meant to be employed for image recognition, and you use it for your very specific detector, and it can happen that these things actually work better than something you would cook up, because the Google guys have spent a lot of effort into this, right, Felix? This is you also did this. You for some of the time series, you just tried off-the-shelf algorithms, and sometimes they actually work very well.
Yeah. I mean, usually if you have some data format which is close to some standard format, like images or time series or something like this, then a lot of the stuff comes out of the box.
And sometimes we still have to tinker. If you have hack-shake detectors, that's something the Google people do not have to deal with. Yeah. So we should think hard about where we actually spend our effort, where our added value comes in, and where we can benefit from Google, Facebook, and Microsoft.
And I also found like starting with something like TensorFlow is relatively easy, but then getting into it and getting to work it, and because it's a bit of an art actually, to get really good results. And this is a bit so the initial learning curve I've always found relatively easy, and then when you want to get really good results, then it gets complicated.
Then you tinker. I agree. Yeah.
So any more questions regarding anything machine learning, physics, general questions?
Yeah, the question on why the interpreter, I guess, is I think for me it's just semantics.
Yeah, I wanted to ask that question actually, because I think it's so fascinating. When the supervised learning is a tool. It's interesting and it's very successful, but it's not that sparkling. Whereas this reinforcement learning or unsupervised learning, this is really fascinating. What comes out or what can come out. And here I wasn't quite sure. There is this interpreter which looks like some external authority that controls the whole thing, whereas I'm not sure this is really required. I think on the other hand side, I said what the only thing that the agent needs is a goal. But who tells the agent that the goal has been reached, right? So at some point, if I think about the game of Go, then there must be the rules somehow, so the machine will, at some point it will just recognize, okay, now I have won the game. But maybe there is always some kind of authority that still is controlling, or is it not?
Nah, I mean, like the rules are basically encoded in the set of actions the player can take. There's this is where the rules sort of enter, and the fact that you won actually enters the reward. If you won, if the game sort of ends and you won or you lost, obviously this has to come with a huge negative or positive reward.
Yeah, but this must be recognized from the environment. Right? So somehow it must be clear that at some point the game is won. So I wonder whether this is just a part of the rules now, or is it part of an external that says, this is now what it is.
No, it's part of the reward. Like the fact that the game ended is part of the reward. What actions?
Who says so?
May I comment? Because actually it's a super interesting topic, and I think it enters also some philosophically very interesting stage, namely, so actually there are some problems which have some intrinsic reward. For instance, if you play a game of chess or so, or some game, then you can just say, okay, the reward is winning the game, and then you can, so to say, back-propagate this reward through every single move you do, and you can say basically every state and every action gets some values assigned depending if they will more probably or less probably lead you to a state where you win the game. So in this sense, there are some problems where this reward is more or less obvious, but any real-world environment, so any real-world problem, for this you have to choose some rewards. So you have to, the person who creates the problem statement has to define some reward function, as the same way as in other optimization problems we define some loss function or some objective function. So in the end, there is always some person who sets the objective, and this is just encoded in this numerical reward function. And also there is a lot of research going on, and I think they call it reward engineering, so especially for this real-world problem like driving a car or so it's autonomous driving. There are concepts like reverse engineering the rewards from the observations you have from good drivers, for instance, so that you reward every action that a good driver would also take.
So supervised reinforcement learning.
Yeah, so I think there's a lot to say about this, and,
Yeah.
but I know way too little to.
Yeah, obviously, yeah.
Wolfgang, could you turn down your input micro level? You are very loud.
I'm sorry.
Everybody else.
Yeah, sorry.
It's still too loud.
Yeah, will do.
Sorry. Yeah. For this reinforcement learning, do you have a kind of a practical problem where this was, say, something you did yourself, where this kind of algorithm was successful?
Yeah, I think Felix, that's also you actually have smarter things to say than myself.
Okay, yeah, I mean, I wasn't yet successful in really operating hard detectors with that, but I think there is one very recent and I think very good example. Namely, it's also a DeepMind project, so from Google. So they controlled this experimental nuclear fusion reactor in Switzerland with a reinforcement learning agent, with a neural network which was trained in this reinforcement learning setup, and this performs better than previously they had some network of PED controllers, which is somehow the standard approach, I think, in this control theory framework. And they showed now that this reinforcement learning trained agent can then, even though it's poorly simulated, trained in the simulation, can on the real actual reactor do this control better than the previous network from these PED controllers. I think this is a very good example. Apart from this, yeah, you're absolutely right that there are a lot of huge successes are just in some artificial environments like playing games. I think this is just now happening, that these successes get transferred to real world problems. So.
Yeah, I posted a link. I think it's, yeah, for the ITER detector, fusion reactor. Yeah, so I think we agree for reinforcement learning, there is actually, like, for real world applications apart from games, it's only starting and it's harder. The hard issues are actually outside of the rigorous mathematical aspects. Right? This is a good executive summary.
I mean, you don't want a nurse being trained like this, yeah. So that you know, then because some of the children have to die before she can learn how to do it better, right? So there are numerous examples where this is just too risky. Yeah. So driving a car, learning from scratch with such an algorithm means you drive it against the wall many times before the agent starts learning how to avoid that. And so, yeah, so in real nature, I think, yeah, it's, as you say, probably you have to start learning on simulated things and then only later go to next phase and then do it on the real world.
Very much agreed. Yeah. This is, I guess this seems to be obviously a good thing to do, the right thing to do. Yeah. And then also, you know, improve your simulation from what you learned, make it more and more realistic, so the machine can learn more and more effects of the real world, and only very late in the game actually go to
all right, do we have any other questions from other persons still in the room, maybe? If not, then I suggest that we close the meeting now, and thank you very much again. It was a really interesting discussion and crash course for people who don't know so much about machine learning, and very interesting aspects for people who already know about something about machine learning. So really cool. And yeah. Maybe as a last word, advertisement, you know, we have all sorts of events. We make all sorts of events. So we have a school. And of course, your institute is, we're very happy to, you know, have you on the management, you know, organizational board, let alone students, that of course anyways. So yeah,
Do you have a web page or something that you can put the link?
And yes, unfortunately, here we are a bit starved. Yeah, web page, not really. Yeah.
I mean, there
we
will
have
be
nothing
there will
like
be announcements at some point, of course, for the
individual. Yeah.
Where is the ÖAW summer school? There is a summer school, right? In
yeah, we have to start organizing. Actually, this is
okay.
This is super late. Last one we had in Vienna because of the pandemic. The one before we had in Styria. We had close to you guys.
Yeah.
And so on. Yeah. But
you're still figuring
invited.
out date and location of that summer school.
Yeah,
okay.
yeah. And we're always happy for people who want to help us with all the organizational stuff if you guys want to.
Yeah, I will
ask
around, definitely.
Wait. Yeah, nice. Thanks.
All right. Thank you very much again.
All right. Thank you.
See you.
Bye. Thank you.